Okay, so now the recording is on. We just double check again, just to be sure the recording is on. Yeah, it's running now. Okay, so as usual, I recommend that you need to get your pen or pencil and paper. Do not attend this class without those two things. You can't learn much by just looking at a screen. It's very rare to find someone who can do that. If you can, that would be great. But for most people, it will not be possible. So it's in your best interest to have a pen and a notebook so that you can do some writing as we proceed. The other thing I'll mention is that a lot of the things we will be doing will depend on what we have done before. So it's important that you review what we have done before so that when you come to class, whatever the subsequent topics do not look scary or strange. Your life will be easier if you try to do the exercises from the previous section and also review the work before you come to class. So I don't know if there are any questions from the class. See, some people are still trying to join. Let's admit them.
Yeah, I have a question.
What's the question?
On under coordinates, there's a remark that you made, and you tried to explain that if you add one more vector to a basis, the new set of the vector is still linearly dependent. And if we exclude one vector from it, the set is still linearly independent. So how comes it's still linearly independent and the first statement says it's linearly dependent, not independent? So I don't know if you missed that or maybe
Which statement?
there's a remark that you made under basis, under coordinates, where you
I think
tried
it's a
to
slide on the
explain.
screen now. The last remark.
Yes. So you
So
see in a remark,
which sentence is the problem?
where it starts, it says, if we add one more vector to a basis, the new set of the vectors is linearly dependent. And if we exclude it, the new set is still linearly independent. How come is still meaning it's supposed to remain linearly dependent, not independent?
So
Or
there's something there that says one more vector.
if
We
we
are
add
adding
one
a
more
vector.
vector to a
Yes.
basis, the
So
new
it's not the same set of vectors anymore. It is a
an extra.
basis plus one more
Ah,
vector.
okay, so if we exclude the one more vector, it now remains
Not
linear.
the one more vector.
Uh-huh.
If you exclude one vector now from the basis,
Uh-huh.
so the new set will still be linearly independent, but will no longer span the vector space.
So we are
So
excluding.
if you have a basis with two elements,
Uh-huh.
if you exclude one, you're left with one element, one
Yeah.
vector.
Uh-huh.
Yeah, so that one vector is still linearly independent, but it does not span the same space as the two vectors.
Okay. Okay. Sawa.
So is there any other, have you understood or you have just given up?
No, I haven't given up. I've understood.
Yes.
Yeah.
Okay. So today we'll start on the subspaces. So subspaces are just vector spaces that are sitting inside other vector spaces. So sometimes you may find subsets of a vector space which are also vector spaces, and such subsets are called the subspaces. We shall see some examples shortly. So to be able to check that an empty subset of a vector space is a subspace, all you need to do is to check two properties. One is that it is closed under vector addition, and it's called closed under scalar multiplication. What that means is that any two vectors from the set, when added, will give you another vector in the set. And if you multiply any vector in the set by a scalar here would mean a real number, you still get another vector in the set. So those two properties are sufficient to check that any subset of a known vector space is a subspace. Of course, there's a lot of theory behind this. Like I said, I've really watered this down so that it can quickly move to applications at some point, or just what you need for the applications. So there's a lot of theory. I will share some textbooks for those who want to go deeper into theory, or if you have any questions and you think more explanation is required, you can say so. So that's basically the idea here. We have a vector space, we pick a subset, and that subset turns out to be also a vector space. So that subset will be called a subspace. So the simplest examples is just the set containing only the zero vector and also the whole vector space. These are examples of subspaces. These are the trivial cases. Remember, in mathematics, any set is treated as its own subset. Every set is a subset of itself. So you can think of a whole vector space as a subset of itself. So it becomes an example of a subspace. The space containing only the zero vector is also a vector space. It satisfies all the properties for a vector space, and therefore it's another subspace of the vector space. So we need to understand that it's not all subsets will be subspaces. Some will not be, but our focus will be on those that are subspaces. So we'll start with some examples in R2, in the two-dimensional Euclidean space. So we'll pick a subset which consists of all vectors of this form, where the first entry is a real number and the second entry must be zero. So of course, this does not cover all the vectors in R2. If you consider only vectors of this form, you leave out some vectors in R2. So this becomes a proper subset of R2. So we want to check if the set containing such vectors inside R2 will also be a subspace. So technically, these are just the points that are on the x-axis because the y coordinate is 0 throughout. What can change is the x coordinate. So these are just the vectors on the x-axis. If you were to think of it geometrically, it's just the x-axis in the Cartesian plane. So we have to check the two properties to confirm that it is a subspace. The first is to check that any two vectors from that set, when added, will give you another vector in the same set. So we try that with two vectors. So we have one vector here and a second vector here. They're in this form. So they could possibly be different vectors. So that's why we have different entries in the first slot. but essentially they must be of this form where the y coordinate is 0. So if we add them, we end up with this vector. Again, this vector has the y coordinate 0, and therefore it's a vector of this form. So that means if you add any two vectors from this set, you will get another vector in the same set. The point you get will still be on the x-axis, as we observe here. It won't move because the y coordinate is still 0. So the second property that we check is if you multiply any point on the x-axis by a number, you still get a point on the x-axis, right? Because the y coordinate will still be 0. So you still end up with a point on the x-axis. So these are the two properties that we needed to check to conclude that the set is indeed a subspace of R2. So there's one more thing we can observe is the following. If any, you can represent any vector in this set along the x-axis as a multiple of this vector 1, 0. So in particular, if you pick the vector, you can just, if the vector is x0, then it's just x multiplied by 1, 0. So what this means is that this one vector spans the whole of the subspace. The subspace is spanned by just one vector. And remember, one vector is considered to be linearly independent, and therefore this one vector is a basis of our subspace T, where our subspace is basically the x-axis or a point on the x-axis. So this is just repeating what I've said. And since the basis consists of only one vector, we say that this is a one-dimensional subspace of R2. Remember, the number of elements in the basis is the dimension of the vector space. In this case, our subspace is spanned by just a single vector. Therefore, we say it's one-dimensional. I think someone is trying to join. Let's admit them. They will miss most of the class if I continue. That's the first example we have of a subspace. We can look at a few more. So it's important that you try to write this, even if it's in rough form, you write it down as you watch. You will learn much better that way. So the next stop is an example, second example. So now this time we look at a different set. This is still a subset of R2, where the y coordinate is equal to twice the x coordinate. So y is equal to 2x. This is basically the line y is equal to 2x. So whenever x is given, the value of y is obtained as twice value of x. So you consider all vectors of this form. So again, this is not the whole of R2. This is just the set of points on the line y is equal to 2x. Here we list a few examples of points that are in the set. So again, two things to check. One is if you pick any two vectors in here and add them, you should get another vector in there. And that is confirmed here. We have this vector, x1, 2x1, and the second vector, x2, 2x2. When we add them, we still get a vector where the y coordinate is twice the x coordinate. So the result is still a vector in the set S, right? The y coordinate is twice the x coordinate. Adding two of them still gives us another vector on the same line. The line y is equal to 2x. So first property is done. The next one is to check scalar multiplication. If you multiply any vector in the set by a scalar, again, you still get another vector in the same set. The y coordinate again is still twice the x coordinate. So we have not left the set. So given that those two properties are satisfied, we can conclude the set S is a subspace. I think this is a mistake. It should be a subspace of R2. So it should be a subspace of R2. I think this is a typo. I'll correct it before I share the slides. So again, you make the following observation. If any vector in here can be written as a scalar multiple of this one vector, and therefore this one vector forms the basis for our subspace. Again, it's generated by exactly one vector, and therefore is of dimension. It's a subspace, and the dimension of the subspace is 1. So is that making sense so far?
Yes.
Good. So you may have noticed one thing. We looked at two
Excuse me, sir.
subspaces. Yes?
Why is the dimension 1 and not 2?
Why do you want it to be 2?
Because 1, 2 is 2D.
Pardon?
I think 1, 2 is 2D, 2-dimensional.
See, like I said, we're trying to make sure you revise. Work. Here is the definition of dimension. The number of vectors in a basis of a vector space is called the dimension of the vector space. That's the definition of dimension.
Oh, thank you, thank you.
So it's really important that you review this. Otherwise, we will keep repeating things that we have already done. Then we'll not be able to make progress. It's important that you take time and review your work before you come to class. It's for your own good. So this one, there is only one vector which generates the whole subspace. So it's the dimension is 1. So we've looked at two subspaces of R2, and both of them turn out to be lines which pass through the origin. The first one was the x-axis, which is a line that passes through the origin, and the second one was a line y is equal to 2x. So in general, any point on a straight line passing through the origin will form a subspace of R2. Any line that passes through origin. If it doesn't pass through the origin, then it fails to be a subspace. Any line that does not pass through the origin will fail to be a subspace. So, and if for some reason you get any two-dimensional subspace of R2, then it must be the whole of R2. The reason for that is that we saw earlier that R2 is a two-dimensional vector space, and that any two linearly independent vectors in R2 will form a basis for R2. So if you, by any luck, come across any two linearly independent vector space, their span will be the whole of R2. And therefore, any subspace of dimension 2 must be R2. So here we consider subspaces of R3. This is the first one. The first one will pick elements in R3 that are this form, where the third coordinate or the Z coordinate, as is usually said, is 0. So the third coordinate is fixed to be 0, but the first two coordinates can be any real number. So again, the same practice, we check if we add any two vectors from that set. What happens? We get the same, a vector in the same set. You can see the result also has the Z coordinate 0. So the next thing we check is scalar multiplication. You multiply any vector in P by a scalar, and again you see that we end up with a vector in the same set. It doesn't we don't get out of a set. So our set is closed under scalar multiplication. It's also closed under vector addition. And we can therefore conclude that it is a subspace of R3. So now we observe the following. Any vector of this form can be written as a linear combination of the vector 1, 0, 0 and the vector 0, 1, 0. So these two vectors are linearly independent and they span P. So that means P is a subspace of R3 and the dimension is 2, because you need only two you need only two vectors to construct or produce elements of P. P is a subset of R3, and therefore we can say it's a subspace of R3. It has satisfied all the conditions that need to be satisfied.
Excuse me.
Yes.
There are some students requesting to be let in to join the class.
Okay. Those are the newcomers. Or maybe failed. And get out. Okay, the training is quite good for this class. I thought people would be running away from mathematics. You have about 50. But you look like you're fans of mathematics. So I think someone else has been kicked out again. Let's just admit them. Looks like it's a new. So this set spans the P, and therefore we can say that it forms a basis for the subspace P. Remember, a basis must have two properties. It must be linearly independent and must span the vector space you are referring to. In this case, our vector space is P, and it's sitting inside the R3, so it is thought of as a subspace of R3. And it has dimension 2. So this is essentially a plane in R3. This is a plane that passes through the origin. Again, I will not focus so much on the geometric interpretation for now, but it's a plane that in 3 dimensions that passes through the origin. Most of you must have done calculus at least the advanced calculus. So you must have done some three-dimensional calculus. So when I talk of the three-dimensional space, I think it should be familiar. So here we go again. Now we consider as a second subset of R3. We call it K. So it's made up of points that look like this. Given any two numbers, this should be X, Y, and R, not R3 here. These X and Y are supposed to be real numbers. They are not vectors. So this should be X, Y in R, not R3. So they should the first coordinate should be the sum of X and Y. Second coordinate should be 2X plus Y, and the third coordinate should be just Y. So here's an example of a point that is in here. So we obtain it by setting X is equal to 2 and Y is equal to 3. Then we're able to compute these values. And we get 573 as one of the points in here. You can create any other point. All you need to do is to pick two real numbers. Once you have the two real numbers, one of them will be your X, the second one will be your Y, and you plug them into here, into these expressions, and you will get a point or a vector inside K. Oh, I didn't draw I've mentioned a figure, but I didn't draw it. So, but again, we go through the same process. We add any two vectors from the same set, and we see that it turns out to be a vector in the same set because it takes the form S plus T, 2S plus T, and T at the bottom, where X is supposed to be X1 plus X2, and T is supposed to be Y1 plus Y2. So essentially, you add these two vectors, you end up with a vector which has the same form as vectors in K, right? Vectors in K, the first is a sum of two, second one is twice the first one plus the second, and the third is just a second number from your pair. So we don't get out. When we add two numbers from the same set, we get a number in the set K in this case. What's left now is to check scalar multiplication. If you multiply any vector in the set K with a number or a scalar, you end up with a vector in the same set. So again, here is another subspace of R3. It satisfies two conditions. So again, we observe the following. If you pick any vector in K, it's possible to write it as a linear combination of these two vectors, 1, 2, 0, 1, 1, 1. So therefore, we can conclude, since these two vectors are linearly independent and they span K, we can say they are the basis for K. And since they are only two, we conclude that B is a two-dimensional subspace of R3. Any questions so far? None. So another way you can build subspaces. Previously, you saw that we would define a set using some linear equations. And then at the end of it all, we are able to show that the same set can be obtained as a linear combination of a finite number of vectors. In this case, it's only two. So it's also possible to start from this point and just create linear combinations of all possible linear combinations of these vectors. They will also form a subspace of dimension 2. So and if you pick any two linearly independent vectors in R3, they will create the linear combinations. Oh, sorry, it will form a basis for a two-dimensional subspace of R3. So you obtain the elements by getting linear combinations of the two vectors. We use this as an example. U is 1, 1, 0, V is negative 1, 1, 0. So these are two linearly independent vectors. We check that if you want to construct the space spanned by these two vectors, you simply get all the possible linear combinations of the two vectors. So they will look like this: some real number multiplied by the first vector and some real number multiplied by the second vector. If you multiply these out and add them out, I think this is switched. The first one should be x minus y because we have a negative here. So this first one should be minus x minus y, not x plus y. The second one should be x plus y. So this should not be minus, should be x plus y. So this should be switched. The minus should be up, the plus should be down. The last one is just 0 plus 0, so nothing changes there. So you can describe the vector subspace that is spanned by these two vectors in this form where x and y are just real numbers. So you could have started from this point and proved that this is a subspace and proceeded to check that this is indeed a basis for the subspace. So, but you can work backwards also, starting from the basis and try to construct some equations that describe some expressions that describe the components of the vector. So that's another way of constructing subspaces. You start with a basis and just try to find a way of generalizing expressions for the components of the vector, as we have done here. So again, this is just the span of the two vectors consists of this one now is correct, is it? No, it's also wrong. The signs need to be switched in both cases. I'll have to fix that. So any two-dimensional subspace of R3 will be a plane through the origin. So the other thing, if you are in R3, you can also work with a single vector instead of starting with two. Fix one single vector and any multiples of the vector, or the set of all multiples of a vector will also form a subspace. And in this case, our vector is 1, our example is 1, negative 2, 0. And any vector spanned by V will look like this. So this is a line through the origin. The set of all linear combinations of this vector is just a line in 3 dimensions through the origin. And the dimension will be 1 because it is spanned by one vector. So in R3, you can have 2-dimensional subspaces. You can also have 1-dimensional subspaces. The 1-dimensional subspaces will just be the straight lines that go through the origin, and the 2-dimensional subspaces will be the planes that go through the origin. If they don't go through the origin, they fail to be subspaces. That can be shown also to be true, but I'm avoiding the extra mathematics that goes with that. So we have been using this term, but maybe it's useful to define it properly. The span of a finite set of vectors V1 up to VR in any vector space Rn turns out to be a subspace. The span basically is the set of all linear combinations of the vectors in B. . So, 'So, 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 ' So initial assumption, okay, initially we don't know whether all these vectors are linear independent. They can fail to be, but if they are, then it turns out that B is a basis for the subspace that is spanned by the set. So if B is linearly independent, then B can be taken as a basis of the subspace. So if you start out knowing that B is linearly independent, you can use it as a basis for the subspace of all linear combinations of the vectors in B. But if it is linearly dependent, then you can progressively throw away some vectors until you are left with only linearly independent vectors that still span the subspace. So this is possible. I hope that makes sense. I've not done any examples of this, but I think it should be logical. If you need examples, you will let me know. So this one, we have said it already. And now the set that contains only the zero vector is considered to be of dimension 0. So now we're going to introduce the dot product. We'll start with the vectors in R2. So if you pick any two vectors in R2, U and V, as shown here, then their dot product is denoted by this. You have the vector U, and then this dot to denote the product, and then V. So again, here I've just, this is the same vector U, and this is the vector V, now written out in full, and the dot is here. So the dot product is obtained as follows. You multiply the components in the first slot, that's x1 and x2. You do the same with the components in the second slot, it's y1 and y2, and then you add. So this sum gives you the dot product of U and V. So you realize that if you get the dot product of two vectors, the result is a number. I think there are people trying to join. Let's admit them. I think some are facing network issues. So this is how you compute the dot product. You simply multiply the components in the same positions, get all those products, and add them. So this gives an example. We have three vectors, U, V, and W. First of all, you obtain the dot product of U and V. So the first thing you do is multiply 2 and 7 to get 14. The second thing you do is multiply 3 and 11 to get 33. When you add them, you get 47. So the dot product of U and V is 47. Like I said earlier, the dot product of two vectors is always a number. There's someone whose mic is on. I don't know who that is. Buya. Try to put your mics off when you join. So this is fairly straightforward. You can extend this to, this is now the second example, but with the vector u and w. Here, the dot product of u and w is 0. This will play a role at some point. When you have a dot product of two vectors equal to 0, it means that they have a special name. We say the vectors are orthogonal. We shall get to that. So this repeats the same thing, but for R3. Again, the dot product of two vectors u and v is simply you get the product of the points in the same position and add those products. Then you get the dot product of u and v. Again, I emphasize, remember, when you get the dot product of two vectors, you get the answer must be a number. It must be a number. So here is an example of a calculation. You can double check and make sure. If we have two vectors, the dot product, you start by multiplying 1 and 4 to get 4, 2 by 3 to get 6, 0 by 7 to get 0. So the sum is 10. And that gives you the dot product of the two vectors u and v. Are we together?
Yes.
So these are very simple concepts, but they are necessary for the work we are going to do later. Make sure you try to absorb them and carry them with you, because we shall need them. We shall be using them freely now in future. And they will be featuring also in the applications. So it's important that you internalize them. So this repeats the same thing I said. The dot product is always a number. Scalar is the same thing as number for us. And you can extend the same idea to Rn, vectors in Rn. So this is just in the general formula for the dot product of two vectors in Rn, where n is some positive integer. I think we have some again. So this now should give you a picture of the general formula, so that the only thing now will change if you, for instance, if n is 5, now you'll have 5 values here to work with, and 5 as well here. If n is 4, it's the same. You have 4 and 4. So once we have the dot product, it's possible to determine the size of magnitude of a vector. And the magnitude of a vector is represented by these two straight lines on both sides. So these two straight lines mean the magnitude or the size of the vector. So that is taken to be the square root of the dot product of the vector with itself. So for instance, if we pick a vector in R2, 2, 7, the dot product of V with itself is 53. And therefore the magnitude of V will be the square root of 53. So this gives you the length or the magnitude of the vector. So this gives an example in R3. We have a vector u. The length of the vector u will just be the square root of the dot product of u with itself. So we proceed and do that here. Is this correct? Yeah, I think it looks correct. 50 plus 9. It will be the square root of 59. That will be the length of the vector u. So there's some benefit to sometimes working with unit vectors or vectors of length 1 or magnitude 1 if you wish. And such vectors have a special name, they're called unit vectors. So if a vector has length 1 or magnitude 1, then it is called a unit vector. And whenever you have a vector, you can always construct a unit vector from it by dividing it by its magnitude. So multiply it by 1 of the magnitude, then the resulting vector will be a unit vector. Let's see if we have an example. Here is an example. So we have a vector v. This is definitely not a unit vector because its magnitude is 3, square root of 3 rather. So that is not 1, and therefore this is not a unit vector. But you can construct a unit vector from this one by using the scalar 1 over the magnitude of v and multiplying it by v. So 1 over root 3 multiplied by the vector v will give us this vector. Now this vector is a unit vector. You can check that its magnitude is 1. So you can check that by hand. It's not too hard. The magnitude will be equal to 1 for this vector. So anytime you have a vector, you can always use this formula to convert it into a unit vector. So this will be useful when we are working with orthonormal bases. We will talk about those when we get there. Orthonormal bases play an important role in almost all of the applications. So it's good to know them. So the next idea we'll explore is the distance between two vectors. So this is basically the same thing extending the same thing you learned in school, the distance between 2 points. So if you want to get a distance between 2 points, you simply get the difference between the two vectors and get the size of that vector, which is and that will give you the magnitude it will give you the distance between the two vectors. So for instance, if I have 2, 4 and 1, 7 as my vectors, I can get the distance between them by subtracting v from u. So u minus z will be 2 minus 1, gives me my first point here. Then 4 minus 7 gives me -3. Now, this is the vector I have as the difference u minus v. So to get the distance from u to v, I just need to get the magnitude of this vector, which turns out to be the square root of 10. So the distance between the two vectors u and v is the square root of 10. So that's how you compute distance. You can extend the same thing to 3 dimensions. The distance between the two vectors u and v is simply the magnitude of this difference, u minus v. And you get that distance to be the square root of 6. So the way it is set up, it turns out that it doesn't matter the order in which you do the subtraction, you will get the same value. Whether you set it up as u minus v or v minus u, you will still get the same answer here. It is possible to extend the same idea to higher dimensional spaces where n is greater than or equal to 4. Nothing changes, you just extend the same ideas to more components in the vector. So Is it okay if we take a 5 minute break or 10 minutes, 5 or 10, or no break?
10 minutes.
10 minutes.
10 minutes.
Okay, so we resume at 7:50.
Auntie.
If you're speaking, you're on mute.
Oh, so I've been talking to myself.
Yeah.
Hey, okay. I have to go a few steps back then. So what to start from here?
Yeah.
So we have just looked at how to compute the magnitude of a vector. A few slides before this. But there's more than one way of measuring the size of a vector.
Excuse me.
Yes.
I think I didn't get something about the unit vector. You said clearly that in order for it to be considered as unit, the magnitude is supposed to be equals to 0. But on the last example where we are getting
magnitude is 1, not 0.
Yeah, 1, I mean, sorry, where we are getting for the non-zeros numbers where we are multiplying 1 over the magnitude of v. Yeah, this one. So you're saying how in this case is this answer a unit vector yet it is not equals to 1?
We didn't say the vector should be equal to 1. We said the magnitude of the vector should be equal to
1.
1. So what you need to do is to compute the magnitude of this vector.
Oh, that is not the final answer.
This is a vector. The magnitude of a vector is, we have a formula for that here. This is how we compute the magnitude of a vector.
Yes.
So you have to do this, what we are doing here,
to
this vector 2, 7. You have to go and do the same to this vector, this one.
The 1 over square root of 3 is of Vilizimejipanga.
Yes.
Okay. And automatically you are supposed to get 1, right?
Let's verify this. Pick your pen and paper and compute the magnitude of this.
Okay.
So a lot of maths, you don't believe anything I say, verify everything. Anything you need to confirm, just pick your pen and paper and compute it. If you have forgotten how to compute it, you can say so that we remind you how. But you must compute if you want to learn the mathematics. You must compute yourself. So is your question fully answered, or you have confirmed the magnitude is 1?
No. Because if I use a calculator, it won't bring 1. So I don't know if I'm supposed to use another.
You don't need a calculator. If you're getting the magnitude of a vector, you get the dot product of a vector with itself, then get the square root of that. Here is an example. This vector is 173. Its magnitude is just a dot product of the vector with itself. Here it is. You multiply 1 and 1, you get 1. 7 and 7, you get 49. 3 and 3, you get 9. And these add up to 59. Your answer is the square root of 59. So the difference is now, instead of 173, your vector is this one. The first entry is 1 over root 3. The second one is 1 over root 3. And the third one is negative 1 over root 3. So get the dot product of this vector with itself, the same way we have done for the previous one. You don't need a calculator for this. It's actually faster to do it without a calculator, because you are multiplying each of these by themselves. When you do that, you will get 1/3 plus 1/3 plus 1/3, which is 1.
Yeah. But the formula, I thought if you see the way it is 1/magnitude of v, then we're multiplying with v. I thought the moment we've gotten the magnitude and we put 1 over the answer, which in this case is square root of 3, and we multiply with v, like that is supposed to be our answer. Like, why are we also continuing again now to square 1 where we are? Kama mi ndo niko confused. Am I the one who is confused?
Mutunga to assist me bwana. Nimefika mwisho. Mutunga is here. Mutunga,
Yes, sir. Here.
utaokoa jahazi hapo bwana.
Yeah. Okay. Let me try to explain.
Uh-huh.
So the thing is, a unit vector, like the definition of a unit vector is that it has a magnitude of 1. So what the lecturer has given here, that is 1/√3, 1/√3 negative 1/√3 is the unit vector. But now to confirm whether it's a unit vector, you have to go ahead and find the magnitude. That is now using the formula that is been using, that is finding the square root of the sum of all the elements. So in this case, it will be the square root. That is now to confirm whether it's a unit vector, you'll have to find the square root of 1/√3 squared plus 1/√3 squared plus negative 1/√3 squared. So you'll get 3/3, which is 1. So you'll have proved that it's a unit vector.
Okay. So, thank you.
You are welcome.
Okay, we can proceed now. So Mutunga, I think you should take over bwana. Upate practice. So where were we? We were talking about orthogonal vectors, eh?
Vector norms.
Under norms, we are talking about vector norms.
No. Oh, yeah, that's correct. So we have seen how to compute the size of a vector using this Euclidean norm, this one in the middle. But it's not the only way you can measure the size of a vector. There are other norms you can use, or the other measures of size that you can use. One of them is the one norm. We shall not use this much. It's useful when there's a certain application. When you're working with the regularization, for sometimes you use the L1 norm. In some cases, it outperforms the Euclidean norm. Then there's also these other mark. We shall not be using this one at all, but it's just good to know them. So the only one that may be, the two that we may find useful are these two, the first one and the second one. We probably will just review this whenever we are applying it. The one norm, it's or sometimes called the L1 norm, and this Euclidean norm sometimes is also called the L2 norm. There's a reason behind the L1 and L2 for those who did measure theory. That might make sense, but you don't need to know the measure theory to work with this. So this is the same thing we have done just before. It's just the Euclidean norm. It's another one way of measuring the size of a vector, but then there are many others. So we have listed two others, the L1 norm and the max norm. but we'll focus on mostly on the Euclidean norm. So this was just added there for good measure. And so that you know about them, so that when we encounter them later, they will not be strange. So the next thing we discuss is two vectors are said to be orthogonal if their dot product is 0. So if you have a set of several vectors, we say the set is orthogonal if every pair of vectors from the set turns out to be orthogonal. Here are some examples of orthogonal vectors. In R2, you can take these two vectors, 1, 0, and 0, 1. Their dot product is 0. So they are orthogonal. So orthogonal is also, if you want to think of it in the traditional way, you would say perpendicular. So the angle between these two vectors is 90 degrees. The same with these two vectors, 2, -1, and 4, 8. Their dot product is still 0, so it means the two are perpendicular. We can extend it to R3 in the three-dimensional space. Again, here we have two vectors whose dot product is 0. And then we have, this is repeated again. I think this is the same example as the first one we did. But basically, if you have two vectors, they will be perpendicular if their dot product is 0. If you want to check that they're orthogonal, just check the dot product. If it is 0, then they are orthogonal. Here is another example of a set from R2, which is orthogonal. You can confirm that the dot product of these two vectors is 0. Here is another set from R3. You can also confirm that the pairwise, if you take them pairwise, their dot product would still be 0. So this is an example of an orthogonal set because every pair of vectors is orthogonal. So another statement that we will make is that an orthogonal set of vectors, if you have a set of vectors that is orthogonal, then that set is necessarily linearly independent. As long as it's orthogonal, then it must be linearly independent. So that's something you can carry with you. Anytime you encounter an orthogonal set, it's guaranteed to be linearly independent. Again, there's a proof for that, but for now, some of these statements, you have to take them as just the truth. If you need more details, for those who need details, we can organize for an extra class just for the details. But maybe you would have to come to Chiromo so that we cover the details. We don't need the details for what we want to do, but for those who are interested, you can let me know. We can always organize for a class in Chiromo when you're available. So you can go a step further for an orthogonal set. If each vector in the set is a unit vector, we say that it's now orthonormal. So from orthogonal simply requires them to be pairwise perpendicular or pairwise orthogonal. But in addition to that, if each vector in the set is also a unit vector, then we say the set is orthonormal. So if a basis is an orthogonal set, if the vectors in the basis form an orthogonal set, we say that it's an orthogonal basis, right? We can also go further and say that a basis would be orthonormal if the set of vectors in the basis is an orthonormal set. We already defined these things. Now we are just applying them to a basis. So here is an example of an orthonormal basis for R2. So these two vectors U and V are orthogonal because their dot product is 0. And both of them have magnitude 1. So they satisfy the two properties for the set to be called an orthonormal set, but it turns out to be a basis also for R2. So we call it an orthonormal basis. So these are going to be very useful. In almost all applications, these orthonormal basis play a role. Is that okay?
Yes.
So here is another example of an orthonormal basis. You can double check that indeed it is an orthonormal basis by confirming that the magnitudes of the vectors are 1. You can also maybe I can give you time to check that. Confirm that the dot products are all 0 and that the magnitude of each vector is 1. So this is an orthonormal basis for R3 because it's a, remember we said any set of 3 linearly independent vectors in R3 will form a basis for R3. These turn out to be orthogonal and must therefore be linearly independent. And since they are 3, they must form a basis for R3. So double confirm that they are orthogonal and also confirm that each is a unit vector, which is what makes the set an orthonormal basis. Tumaliza mnasema, tuendelee.
Yes, it's true.
Good. So now we have given an example of an orthonormal basis in R3. We have also given an example of an orthonormal basis in R2. You can extend this to any dimension. So the reason we bother with all this is because if you have an orthonormal basis, the process of computing the coordinates of any vector becomes easy if the basis is an orthonormal basis. We'll see that in a short while. So we consider R3. So many times we wish to compute the coordinates of a vector using a given basis. So this we have seen before is an orthonormal basis. And now we want to get the coordinates of the vector W with respect to this basis. But since it's an orthonormal basis, there's a shortcut to getting the coordinates. So if you want to get the coefficient of U1, simply get the dot product of U1 and W. That will give you the coefficient. Want to get the coefficient of U2 in the linear expansion. This is just a dot product of U2 and W. You do the same with U3. Get the dot product with W, you get the coefficient for U3. We'll see how that works in the next slide. So the coordinates are as follows. W dot U1, the dot product of W and U1 is 1 over root 2. You can confirm that. The dot product of W and U2 is 0. And the dot product of W and U3 is 9 over root 6. So this now become the coordinates of the vector W with respect to the basis B that we had set up. So, but now remember, once you have the coordinates, now it's possible to express W as a linear combination of the basis vectors, but now these coordinates are your coefficients in the expansion, in the linear combination. So 1/√2 is a coordinate for the first vector, 0 is a coordinate for the second vector, and 9/√6 is a coordinate for the third vector. So if you can confirm that that is the case in your own time. Just double check that indeed, if you multiply U1 by 1/√2, multiply U3 by 9/√6, and add them, you should get W, where W is already given here. So, but the import of this is that computing the coordinates of W with respect to the orthonormal basis was just as simple as getting the dot product of W and U1. Now, I must emphasize that this only works. It can only work if the basis is an orthonormal basis. If it is not, you cannot use this technique to get the coordinates. Mwaigwa? Eh? Hakuna watu wa mlima hapa bana. Iwinjo. Ama niko peke yangu kwa darasani bana.
There are some people waiting on the lobby to join.
I need to do some research on how to make at least 1 or 2 people admins. That's why they can admit people. I will do that. I promised to do that last time, but I did not.
You can simply click on the 3 dots and make a presenter.
It's not giving me that option. I have tried. There must be some other way. We'll figure it out. So there you are. Have you double checked that this is indeed an orthonormal basis and that these coordinates are correct?
We're checking.
I think we can leave that as an exercise for you to check. In your own time, you can let me know. So the next thing, we shall not do this in detail. It's a Gram-Schmidt algorithm. It says the following: if you have any set of linearly independent vectors, then you can use this algorithm to turn it into an orthogonal set, and eventually you can turn it into an orthonormal set by normalizing each vector. So we may need this algorithm later on when we are dealing with the symmetric matrices. the eigenvectors of symmetric matrices. So we might use this. We get there. So basically, this is how you compute, you convert. If you have a set of linearly independent vectors, V1 up to Vn, you can convert them into another set of linearly, or rather of orthogonal vectors, W1 up to Wn, which still span the same. They will also be a basis for the same space. You will still span the same space that is spanned by V1 up to Vn. So how to compute these W1s is you set the first vector W1 will just be the first vector in the list. You can obtain the second vector W2 using this formula. You get a dot product of W1 and V2 divided by the norm of V1. So this becomes your coefficient. Multiply that by the vector V1, subtract all that from the vector V2. You get your second vector. You keep doing this. This gives you the third vector, and in general, the kth vector in your list is obtained using this formula. And maybe it may be a good exercise for you to try to turn this vector into an orthonormal, this basis for R3 into an orthonormal basis. So this is the last slide I have. I'm preparing the slides as we go. Maybe I will prepare a complete example for this Gram-Schmidt algorithm and add it to the slides before I share. Then the next topic we'll go to is matrices. Matrices are mostly familiar with most of you, so we should be able to go through that quickly. So what I propose is you try to master this first part of the content that we have done this week and last week. It's a good idea for you to do a thorough review of this part, because everything we have done here is just it's everywhere. Everywhere you will meet it. Most of the stuff we've done here, you will encounter it in most of the sections that we are going to move to now. So you must master this. Otherwise, you will be pushing us back and forth again to redefine some of the older things. So it's better to read before you get a lot of volume. If you have a lot of volume, it will be impossible for you to absorb some of the concepts, especially those of you who have been out of touch with the maths for a while. If you don't give it the time, you will have trouble in the future topics. Are there any questions? I would like to stop there for today. I will share the recording. I will also put together a few questions and I'll forward to Kibet. So magnitude and norm are the same thing in our case. What is the thing is, there are different ways of measuring magnitude. They all measure different things. They don't measure the same thing, but they all count as magnitude. So it depends on what you want to achieve. So for us, we've been working with the Euclidean norm, which is just the standard way of measuring distance. So the other ways to measure distance, which are a bit abstract, they may not be easily understandable, but they are useful. So this one, just take it as another way of measuring the distance. These are all magnitudes. So if you choose to work in the L1 space, this is how you will measure distance in that space. It will also affect your calculus. It will affect all your concepts of continuity and so on, because they all depend on how you measure the distance. So if you for those of you who did metric spaces, you probably had different ways of computing distance. The metrics you're working with were some distances of there are different kind of metrics you can work with. If you did metric spaces in at the University of Nairobi, I think if you did them, you covered them in third year, SMA 301. So here, don't overthink this. They're just different ways of measuring distances. The one that we shall work with most is this one. The other one that will be useful is this one norm, which is helpful when you're working with regularization. For instance, if you're working with regularization for linear regression, you will need the one norm. Sometimes the one norm outdoes the Euclidean norm performance. Not all the time, but there are situations where, especially when you're working with sparse matrices and so on, this L1 norm turns out to be quite useful. So don't overthink this. When you see norm, just think distance. Or magnitude, if you like. I think magnitude is more appropriate. Is there any other question?